Do you know what are the internal process flow that executes sequentially during the SPICE simulation? Do you know what are the two fundamentally different SPICE simulator exist in VLSI? In this video, you will get familiar with electronic components nomenclature basics. So stay tuned, stay focused. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the SPICE simulator types, that is, the difference of look and feel. There are several types of SPICE simulator and we will differentiate them in terms of look and feel. Next, we will point you out to the episode which has the NGSPICE installation instruction demo and the necessary links. Next, we will talk about the internal flowchart or the process flow of the SPICE simulator. This is a generic one and this could be applied to any of the educational as well as the industrial SPICE tools. However, there will be some additional steps in case of a industrial SPICE tool that is specific to a particular EDA vendor, and hence we will not be able to give you the minute details of such industrial SPICE tool substeps. Next, we will dive into the SPICE fundamentals and we will start with the element notation and unit. Next, we will go further deeper on the SPICE fundamentals for the element and symbols. Next, we will go further down in the SPICE fundamentals and we will talk about element notation and unit. Finally, we will dive into the SPICE deck details by sharing the basic informations of the title and the end comments. By the title and end, as well as talking about the comments. Now, that's the menu for today. So without any further delay, let's begin. SPICE simulator types, look and feel. Based on the usage of the SPICE tool, there are two broad categories of the SPICE simulator. Basically, these are the two different user perspective or user usage perspective, else there is a division. So the first one is the netlist based, where we have to write a particular SPICE netlist in text form and simulate it using the particular binary. Like we have used NGSPICE in first couple of episodes of this series as examples as I have shown. The next category is the schematic based, and here the candidate is LTSPICE, which is a free tool. We are not covering the LTSPICE in this series. We are covering rather the netlist based SPICE tool in this series because that is the very much fundamental thing. Even you are using a schematic based SPICE tool, under the hood, it actually is simulating a netlist that is generated by this particular schematic tool. The schematic tool at the bottom even uses a binary to simulate the SPICE deck that it builds from the schematic. So in this series, we are going for extreme fundamentals of the netlist based SPICE tool because this is where you start learning in your undergraduate college level, and this is extended for the various electrical characterization in the VLSI domain, as I have explained in the first episode. And the schematic based drawing is for the analog designers who design the analog circuit from the schematic, and this could be a IP level development, it could be a block level development, or maybe for a data design. So that's the basic division or the categorization of the two different SPICE tool available in either in the open and free software or in the VLSI commercial EDA tools. So both have the same kind of divisions. That means the netlist based SPICE tool and the schematic based SPICE tool. We are done with this particular slide. So let's move on to the next slide. Since in this series we will be extensively using the NGSPICE, as I have demonstrated in the last episode with few examples, the installation episode of NGSPICE we already have published even before releasing this series as a episode, and here you can see the thumbnail of that particular episode. You can find the direct link of this episode in the description of this particular video. There is nothing more to say on this, so let's move on to the next slide. SPICE simulation internal flow. Now we are talking about the netlist based SPICE tool internal flow. Here, once you provide the netlist to the simulator, it parses it, and what happens inside the SPICE tool? The reason behind keeping this slide is that once you find a fault or error or something unusual, you have to go back to the different internal steps and check from where this particular unexpected thing, whether it is an error or unexpected result, it is getting generated. The first step is to read the SPICE deck and the .include file. So inc.inc is the shorter form of the .include that is used to include many files like models or libraries in the SPICE deck. So in this way, our flowchart will go up to down this direction only. So we'll proceed in this manner for the left hand side of this arrow as well as in the right hand side of this arrow. Next is the init numerical engines. There are several numerical methods that you have learned in your undergraduate level like bisection, Newton-Raphson, all these things. In this particular SPICE simulator or any of the SPICE simulator which is a netlist based, there exist all these numerical methods and they are intelligently picked for case-to-case basis, or even there could be a switch or a option to select a numerical method explicitly by the user. So this could be there, and this is for the initial solution, that is the initial condition solution that is needed in a SPICE deck. We will go in detail of this init and all these things in the fundamental episodes in the upcoming episodes of this particular series. So wait for that, we will go in detail. Now let us go to the next step, that is the not set or IC initial OP guess. So there are two different kind of initialization. One is not set, another is .ic, and there could be some files associated these two also. So once we go in detail of these things, you will see and know about these details. This is because here we are giving the bird's eye view of the flowchart and we are not going details of each and every step because we have episodes later in this series to cover all these things in detail. The next one is the DC bias convergence that happens inside a simulator, and this convergence is based from the numerical engines which is picked by the simulator or it may be specified by the end user. The next one is the AC, DC or transient analysis. So that happens inside the SPICE simulator. These are the basic three type of SPICE analysis that is being used on a particular circuit under test, the circuit that you design in the SPICE deck. Next one is the calculation of @node and @time, frequency and param steps. So all these things are there. Next is the data matrix mining. So what is data matrix mining? So there will be, let me draw a diagram here. You will understand better with the diagram. So there are several nodes in the circuits, right? This is a node, this is a node, this is a node. So these are the nodes where the different components are interconnected. So there are several nodes like this. So all these have to be solved in a matrix method, and that data has to get mined in some data structure which is defined internally to the SPICE binary. So in this step, the data mining will happen and the dynamic calculation, that means the calculation with respect to the time, will be done by the SPICE simulator, the numerical methods inside it, and so on. Next step is the waveform DB creation. Once the simulation has started, right, the data mining has started, the visual output, that is the data, whatever goes to the output nodes of the circuit, will be stored as the waveform database. Now, waveform database is nothing but a database which contains the voltages, currents, etc. with respect to the time. That means the time in the x-axis. So this is a xy axis. So in this axis, there will be time. In this axis, there will be current and voltages. So all those things will be stored in the waveform DB, and from one simulator to another simulator, this waveform DB is different. For Verilog, there is a file called VCD file. We have already covered that in the Verilog series, and that is a similar kind of waveform DB in the digital simulation. And in analog simulation, there will be .db file, or maybe some DB name will be there, or it may be .raw file. From there, you have to pick up the data. In case of NGSPICE, we have a very easy option to plug in the GNU plot and directly throw the output into the GNU plot GUI, where it shows the current voltage characteristics with respect to time as graphical plots. Multiple windows are plotted as per the instruction. We have already shown this in the last episode. There are 3 circuits we have shown, the different graphs we have shown, already it is there. So for NGSPICE, you don't have to find the DB, but also we have mentioned there is a temporary DB file for the GNU plot. I have pointed out last episode where I have shown the hands-on demo of the 3 SPICE circuits. The waveform DB is created. Next, we have the text output log file. So this is a log file where all these steps, when they are getting performed, all the details of those steps are logged into. That means they have been written in detail. So in case our end user is facing some issue or there is some question, there is some query, you can go to the log file and you can read it and reach up to the particular point where there is your necessary information which you are looking for. The next step is the dot measure execution. Once this waveform DB is already completed, right, there will be a dot measure execution that will happen internally. Although this is not that you will completely see this is finished and this has been executing after that, not like that, but internally somehow it manages to perform the different electrical characterization on the waveforms of the SPICE circuit output. And dot measure command, these are given to characterize electrically the different current, voltage and extracting different data from these IV characteristics. Okay. Next is the alter statement, and it's a special statement that helps to repeat different block of codes with a minor change in it. So you don't have to write 10 SPICE deck, instead you write 1 SPICE deck and there you repeat a particular block where there is a small change, and for that different set of results will be generated. That is the alter statement. We have this in NGSPICE. And next step at the end is stop. So once all these things have performed, right, all these steps one by one have been performed, the simulator stops and exits from the simulation. So folks, these are the basic internal steps of SPICE flow. So there could be some small additional steps in the commercial or the industrial SPICE tools. Obviously, you will have these kind of extra knowledges from their respective manual. That means the commercial SPICE tool will have a manual and you have to look into the manual. So where there is a difference, because this is what is a basic common structure, this will be there. In addition, there could be something that a commercial SPICE tool might have. Those informations are available in the latest manual of that particular SPICE tool. So we are done here. So let us move on to the next slide. So in this slide, we are not showing anything. It's just an interconnecting slide, and this is kept to make you understand that now from this particular slide or the next slide onwards, we will be deep diving into the SPICE fundamentals. And in the next couple of episodes, we will swim through the deep fundamentals of SPICE. That means those are beyond necessary in SPICE. You have to know them in detailed manner. So without any further delay, let's dive. Element notation and unit. Now this is a table, right? And there are 1, 2 and 3 examples are there. So let me point out first element symbol. Here you can see RLC. You can see this is the RLC. Now you can see L, P and R. These belongs to the inductance, capacitance and resistance. And there is a number, right? Generally this is a number. There are 10 inductors. So there will be L1, L2, L3 and it will be up to L10. So like that it is named. Now there is node 1 and node 2 because this L, C and R have only 2 nodes or 2 legs in the physical component. So they will be connected to different nodes. I said already, right? Here some components are interconnected, here some components are interconnected. So like this, there will be a nodal analysis in the SPICE internally. So for that we have to define the nodes, and this is the first node, this is the second node, right? This is 1, this is 2, node 1 and node 2. And here you can see the set of node 1 and set of node 2. In case of MOSFET, there will be drain, source, gate and body. So there will be 4 nodes for a MOSFET. So there you will have 4 nodes here, 1, 2, 3, 4. And hence to accommodate we have node N. That means it could be more than 2 nodes. It could be 3 nodes like transistor, the PN junction transistor or the bipolar transistor, right? There will be emitter, collector and base. There will be 3. So after the first 2, there could be 1, there could be 2. So n number of nodes could be there. So hence we keep this node n. Now let us look at the value and the suffix which is kept here, and here you can see A dot B. The unit will be Henry. So L is Henry, C will be Farad, R will be ohms, and so on. So we will come to this all details in the upcoming slide. So I will not exhaust my energy here in this slide. So let us carry forward our energy to the next slide. Element and symbol. Here we will talk about the details of the elements and symbol. As I said, BJT, right? Bipolar junction transistor. Q is written there. So this is a convention, and in SPICE, you cannot randomly write anything for any component. So you have to follow this nomenclature. JFET will be J, MOSFET will be M, gallium arsenide MESFET will be B, diode will be D, resistor will be R, capacitor C, inductor L, and transformer is K. So these are the initials. The next continuation is like this. There are 4 control sources, right? They will have this symbol. So VCVS will have E, VCCS will have G, CCCS will have F, and CCVS will have H. The current source will be I, the voltage source will be V, and the control switches will be W, and the transmission line will be T. So this is like when we are writing a SPICE deck, there will be some lines that begin with, say, voltage source or the current source. So it will be I, say IDC we write, or I10 or I5, something like that we write, and for voltage we write similarly like VDC, VDD, all these things we'll write. These are used as the first character of the line. So these are the first characters of any line that you write in a SPICE netlist for the components. So we are done here. Let's move on to the next slide. Element notation and unit. The first is the A part, and then there will be the B part. So here 10 to the power minus 15 is written as femto, capital F. Minus 12 in the power of 10 will be denoted as pico. This is nano. This is micro. And there is a word milli. Okay, don't confuse this with the milli. Milli is coming in the next one. In the SPICE deck, if you see, there is a unit milli. That is not the milli. That is not milli. Milli is something else. So milli is this and milli is this. So you have to remember this. And as we proceed in the plus powers, so 10 to the power 3 is kilo, 10 to the power 6 is mega, 10 to the power 9 is giga, 10 to the power 12 is tera. Sometimes the giga is pronounced as giga also. So some countries they call it giga, and some countries it calls giga. Both are okay. The next one is the B part, that is the A dot B, which we have seen in the previous slide. And here the units are volt is B, ampere is A, hertz is HZ, ohm is ohm, Henry is H, farad is S, degree is dec, and second is S. So these are the units. So it will be like femtofarad, FS. So there will be millivolt, MV. There will be nano ampere. So that will be NA. Okay. And there will be kilo ohms. So that will be the total unit. That means the A part and the B part will make the unit complete of any component. We are done here. Let's move on to the next slide. Now in this slide, we will talk about the title and end as well as the comments. And this we will do in this slide as well as in the next slide. So let us start. The title line must be the first line in the input file. It contains are printed verbatim in the stdout log file. So this line starts with the star, right? And whatever after star is printed as is in the log file or as well as in the screen, that means the output terminal. So it could be done using the dot title statement also. Comments are like the star, and after anything star is taken as comment in the SPICE deck. The asterisk is in the beginning of the line indicates that is a comment. That means if you have to comment out any particular, say, analysis or component, you have to just put a star in front of the entire line, and that will be commented and that will not be considered in the SPICE simulation. That means the asterisk makes a line inactive to the simulator. End of line comment, or you can say it as an inline comment. End of line or inline comment is like that, couple of commands or components like, and then we have a dollar, and then we have written something in words. So anything like in this fashion, this part will be treated as inline comment or end of line comment, whatever you say. Both are used terminologies in world of VLSI. The dot end line must always be at the last of the input file. So this is the marker that tells the simulator now you have reached the finish line of your running. So you are running for so long and now I give you the flag to stop. So this is a finish line marker for the SPICE simulator. general form dot global and then node name. There could be some global things that may be used in a circuit, and those are defined by the globals. We are done with this particular slide. Let's move on to the next slide, where we will continue with some of the examples of the things that we have spoken here. Let's move on to the next slide. So here are the examples. First, the title. You can see that dot title, and then we write test of the tile line. Whatever written here comes as the first line of the terminal output or the log file of the SPICE tool. Next, example of a comment. Here you can see star, then RF equal to 1K gain should be used for 100. So this is a comment, and this is the instruction to the designer. Next, check open loop gain and phase margin. Okay, so all these things have to be checked, right? Examples of inline comment is like that. RF2 equal to 1K, then dollar gain should be 100. So this part of this particular SPICE line is comment. Basically anything that is beginning with dollar in between a line is comment. So this part is commented out. Up to this will be read by the SPICE simulator. Let me clean it and say it again. So this part is processed by the SPICE simulator, while this part is excluded from the SPICE simulation. So this is treated as inline comment or end of line comment. Here you can see C1 is 10p, check the open loop gain and phase margin. So this is a comment or instruction for the designer. And here this part will be processed by the SPICE simulator, and this part will be excluded by the SPICE simulator. Examples of the dot statement is simple, the dot end. There is nothing more. After dot end there is nothing, so it is ending. We don't have anything after dot end. And we have the example of dot global. Dot global means we make some node global like GND or VCC. This is a global node, and anywhere they will be pointing to the same particular node, because say ground is the common ground of the circuit. So we have a big circuit. We have smaller blocks inside there. Everyone will be connected to the basic ground. So the basic ground is the same. So here ground is global, and VCC, the basic power supply that is coming, right, that will be even common to all of the block, that is global. So we make these two things global. Anywhere we write GND or VCC, they will be treated as global. So these things are very common thing in a SPICE deck, and we have started to jump into the basics and fundamentals of SPICE, and in upcoming episode we will continue this deep diving, which is a very basic thing to know, because without that you will be unable to troubleshoot any design that is written in SPICE. In industry, either you go for the IP characterization side or you go for the analog design and characterization side, you will face definitely SPICE netlist. The netlist could be in this particular form or maybe simulator specific form, but anyhow you will face them. So for that we have to know all the details of the SPICE fundamentals. We have started from this particular episode, and we will continue this saga in the upcoming episodes. So we are done here. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.